Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created bunch of playlists covering various categories of the problem such as breadth first search, depth first search, sorting, binary search, trees, graphs, arrays, strings and so on. So please check them out as well. Also, I have uploaded the code for this particular problem to GitHub page. So you can get the link from description below this video. Let's go ahead and jump into today's problem. In a town, there are n people labeled from 1 to n. There is a rumor that one of these people is secretly a town judge. If the town judge exists, then the town judge trusts no one. Everybody except the town judge trusts the town judge. Looks like that. There is exactly one person that satisfies properties 1 and 2. You are given trust, an array of pairs where trust of I is AB, representing the person labeled A trusts the person labeled B. So if the town judge exists and can be identified, return the label of the town judge, otherwise return -1, right? So basically there are n people labeled from 1 to n. Okay, so there is a trust relationship that is given in a trust array. Okay, so that is a two-dimensional array where the first thing represents the person who is trusting and the second one represents the person who is trusted. So basically those are represented by A, B, right? So A trusts B, that means simply. So there is some kind of graph that forms. Basically A trusts B, A could trust C, or B could trust C, C could trust D, something like that, right? So there is a graph that forms, but the graph is not a transitive based. So it's not like A trusts B and let's say B trusts C. So it doesn't mean A trusts C. Okay, so the assumption is not true. That is what when I said transitive is not allowed, right? A trusts B means just A trusts B, that's it. B trusts C means only B trusts C. So if we are given with A trusts C explicitly, then only we have to assume A trusts C. So whatever the trust relationships that are given in the trust array, right? So only those hold good. So there is no transitive. So no transitive. So this is what we need to identify. So since there are no transitive, the relationships are not transitive. So whatever that are mentioned in the trust array, we just have to take as is. Okay. So A trusts B is A trusts B. It's never A trusts C from this relationship B trusts C. Okay. So now that we clarified the transitiveness of the trust, so let's go ahead and look into the second one, right? So everybody trusts the town judge. So that is what is another thing. So there are n people, somebody trusts somebody, right? So that's one thing. But in that somebody, at least one of them is town judge. That's what is given. There are cases where there is no town judge also. That means if the town judge exists, that means the rumor may be not true, right? There is a rumor and one of these people is secretly a town judge, right? So that rumor may be, it's just a rumor. That means there is no one in that town as a judge basically. So in that case we would return -1. So if we are sure that this guy is a town judge and he is trusted by everyone, all the n-1 people, right? Then we can easily identify, okay, this guy is a town judge. And so we were given like, okay, there is absolutely one person as a town judge, right? So there is a rumor with one of these people. So if it happens to be like all people are trusting two people, right? So that means n-2 people are trusting these two guys. That means we cannot identify again as a single person as a town judge. So there are several cases possible. So in order to cater to all the different cases, right? So there are 0 town judges, there are 1 town judge, there are more than 1 town judge. So that means if there are 0 town judges, that means there is no town judge at all. we will return -1. And if there is one town judge, that means well and good, we identified that one person. Good, we just return the label of that person. But if there are people who are trusted by all of them, right? So there are two people which are trusted by all of them. All of them means n minus 2 people basically. These two people, if these two people there is a trust relationship, right? Again, that means we will come down to there is only one person which trusts all of them, right? If there are two people trusted by all the n minus 2 people, then also we cannot come to a single person, right, who is trusted by every single person from 1 to n minus 1, assuming that nth guy is a judge, right? So these are all the cases that are possible. So what we are going to do is, first we will prepare a list or a map of people along with their trust relationship, right? So if this is example 1 trust 3, 1 trust 4, 2 3, 2 4, 4 3, right? So the trust relationship map will look like this. So 1 is 1 trust 3 and 1 trust 4. So we will do 1 trust 3 and 1 trust 4, right? So and 2 also trust 3 and 2 also trusts 4, right? So 3 doesn't trust anyone. So one of the judge quality is town judge trusts no one. So 3 is a possibility of a judge, right? Because 3 doesn't trust anyone. Next, go on. 4 trusts 3, right? So if you look on to the right side, right, the right side, so 1 trusts 3 and 4, 2 trusts 3 and 4, 3 doesn't trust anyone, 4 trusts 3. So we know that 3 could be the candidate for judge because he doesn't trust anybody. So the number 1 is satisfied. We are saying a town judge means number 1 and number 2 from the left side, right? So these two should be satisfied, right? So 3 satisfies this one. He doesn't trust anyone. So that's one is satisfied. And everybody trusts the town judge. So try to find out if 3 is there in the trust map of everyone. So for 1, does 1 trust 3? Yes. Does 2 trust 3? Yes. Does 4 trust 3? Yes. So in that case, all the other n minus 1 people trust 3. So for this, what we say, judge exists, right? And answer is 3. That is what we are going to do. So basically, what we are essentially doing here is we prepare a map of people and their trust, right? And people and the people, list of people whom they trust, right? So this is people, the person 1, and this is the list of people whom he trusts, right? That is the kind of map that we are going to create. Once we have that map, then we go through starting from 1 to n person, right? So because the labels are given as 1 to n, not from 0 to n as suppose, right? 1 to n. So we go through 1 to n. For the purpose of keeping track of the trust relationships, right, we put a hash set, okay? We keep track of the people in the hash set. And once we go through from 1 to n, if the persons are not existing in that hash set, right, then we will remove, okay? And finally, we should be left with one person who is trusted by everyone. If that person is not trusted by everyone, or if there are more persons trusted by everyone, then we will have to return as -1 for the answer, okay? So let's try to work out these steps from this map. So now that we already said, okay, judge exists and answer is 3, but let's try to work out through the steps, right? So this from looking at the map, we were able to come up with the answer as 3, right? But now let's go through these steps and try to come up with the answer. So now we are initializing the hash set, okay? So hash set, which is initialized to nothing. Now, so to start with, we start with the first person, right? That's what we are going to do, right? 1 to n. So 1. How many people he trusts? 3 and 4. So add 3 and 4 into the hash set. So now hash set becomes 3 comma 4 after 1, right. So now 2, when we come to 2, see if there is any intersection between the people trusted by 2 and whatever the things that are there in the hash set. So you intersect hash set with the people I, right, people trusted by people I trust, I will say, okay, people I trust. So that people I trust is basically this one, the right side in the map. So now when we are at 2 trusts 3 and 4. If we take intersection between people trust 3 and 4 here also, right. So 3 and 4 and 3 and 4, the intersection is again 3 and 4. So we don't need to update the hash set. So far we have 3 people, right, and 3 for 3, right. So for 3 he doesn't trust anyone, right. Let me go back, sorry. So 3 doesn't trust anyone, right. So when we prepare the map we won't have anything, right. So we don't have to create this particular thing because there is no trust relationship in here. So this is just for our understanding. When I was going through the example, I created. So but when we create the trust map from this, right, so it is just like this. So now we go to 4th. It is only 3. So now if we take the intersection between 3, 4 and 3, it's only 3. So now I change the hash set to only 3. So after going through the entire set, we are left with the hash set only with single person, that is 3. So now this is the answer we return, okay. So that's how the algorithm is going to work. Let's go ahead and try to understand from the code perspective now. So as I said, we are going to create a map of trusts. So this is a person and this is a list of persons whom he trusts. So I am creating a map and I am taking the length of the trust. So this is just a base condition. If the length is 0, that means you don't have any trust, but n is given as 1. That means there is only one person in the town and he doesn't trust anyone because this is only one person. So he ultimately becomes the town judge, right. So this is a base condition. That's why I have it. If the length is 0 and n is equal to 1, you just return 1. If n is greater than 0, n is greater than 1 or length is greater than 0, we will come to this for loop and try to build the map, right. So this one we are building the map, getting the A, B and trying to build the map, right. So now after this for loop, we will have a map which is similar to this, right, what we built, okay. And next, as I said, we will declare a hash set and we will call it as judge, because that is what the final thing that we are going to look at. And we will see if judge is initialized or not. So this is just a variable that I am keeping just to keep track whether we found any judge yet or not, right. So next one. So we go through 1 to n simply because the labels are from 1 to n, okay. And if the map contains I, that means he trusts someone, right. That means if a map doesn't have a person, right, he doesn't trust anyone who is a right candidate or possibly right candidate for the judge, right. That's why we are making sure if the map contains this person. If it contains, and we check if the judge count is 0 or not. So number of people who are in the judge. If it is 0 and we have not initialized judge, then we are going to initialize the judge with the corresponding trust for the person I, right. And then we set judge initialization happen to true. But if the judge initialization happened, but through some intersection the judge count became 0, right. That means at some point in time there is a person who trusts a set of persons and there is another person who trusts another set of persons. That means two people trust a set of people which are different. In that case, there is no common guy who is trusted by two people. In that case, the judge becomes empty, but judge is already initialized. In that case, we are going to return -1 then and there. But if the judge count is non-zero, what we are going to do is, just like we did the intersection, we do the intersection between the judge and the current number of trustees, okay, the person trusted by, persons trusted by I, right, persons trusted by I. So, and reinitialize the intersection, judge hash set with the intersection. That's what we were doing, right? So, initially when the intersection we took between 1 and 2, it is 3 and 4. We just keep the same thing, 3 and 4. But when we intersected 3 and 4 with 3, we changed the hash set to have only 3. We removed 4. In other words, we just reinitialize the judge with 3. So, that's what we did. So, that's what I am doing in this. So, first calculate the intersection and check whether, put the intersected values into the judge. So, this will go on from 1 till n, right. So, finally, check if the judge count is 1 or not. As long as judge count is 1, we are good. If it is less than 1 or more than 1, that means we are not able to identify a judge from the given input, right. As is said, there is only one person, exactly one person, that is what it said, right. There is exactly one person that satisfies 1 and 2. That is, he does not trust anyone and he is trusted by everyone, like that. So, if the judge count is not equal to 1, we just return -1 simply. If it is 1, obviously we just return the first guy because it has only one entry, right. So, that is how we are going to solve this problem. Let us go ahead and try to look at the time complexity and space complexity for this particular algorithm. So we are saying, let us say the length of the truss, right, length of the truss as m, right. So, m is length of truss. So, n is already given, right, this one. So, we are going through the length of the truss here. So, that becomes order of n, right, and we are going through again 1 to n again in this for loop, right, we are going through 1 through n. So, this will be order of, we will call m, right, that is what it is, and then order of big N, because that is what the input parameter is. So, that is what is the total time complexity for this particular algorithm. So, if you take order of m plus n, so that is the total time complexity for this algorithm. So, where m is the length of the truss, n is the number of people in the town, right. So, typically in a best case it is n minus 1, because obviously we have one judge, right. So, we go through this 1 to n, that is the reason why we will take just for order of n, order of m plus order of n, which is totally order of m plus n, that is the time complexity. So, let us go ahead and look at the space complexity for this algorithm. So, for the space, since we are building this map, right, so a map of people and their trust relationship, right. So, map for people and their trust relationship, and is there anything that we are using? Yes, we are using the judge hash set, right. So, judge hash set depends on the maximum number of people trusted by a single person. So, since we do not know the maximum number of people trusted by a single person, right, order, let us say order the average number of people trusted by a single person is p, okay. So, the average number of people trusted by a single person is p. So, that means the space complexity needed for this hash set is order of p, okay. And we are using the dictionary, the map, right. So, the map will have n elements in it, right. Of course, if there is one judge, there will be n minus 1. So, since we are only subtracting 1, we just can say just n, right, n entries in the map, and each person could trust n minus 1 people, right. Each person could trust n minus 1 people, right. So, that means order of n into n minus 1, right. So, this will take order of n into n minus 1. This is worst case problem. So not the best case. For example, if we look at the, let's go with the capital N because that's what is given, right? So yeah, what I was saying is this is the worst case. That much we need, right? But if you look at this example, right, how many trust relationships it has? Even though there are 4 people, it has just 5 relationships. It's not exactly 4 into 5, right? But the maximum relationships that this map could store or the input could have is n into n minus 1. That means a given person trusts all other n minus 1 persons, right? So if it happens for every single thing in every single person, right? So the maximum space complexity that this map would need is order of n into n minus 1. That is order of n square, we can simply say. So this is, since we are talking about big O notation, right? Order of n square is what we are going to say as time complexity for the dictionary. But there is a time complexity for this order of p. So plus order of p. But in general, the order of p could be equal to, if there is a scenario, right? If there is a scenario, a person is trusting every other person in the town. That means there are n minus 1 people, right? So that means here p is actually n minus 1, right? So if you take those worst case things, right? So order of n square plus order of n minus 1. So totally what we would say is order of n square is the space complexity required for this particular algorithm. Okay. So if you have any questions, please post them in the comment section below this video. I have posted this code to GitHub repository. You can find the link in the description below this video. If you haven't subscribed to my channel yet, please go ahead and subscribe. Also share among your friends. Please click on the bell icon so that you will be notified about my future videos. Thank you for watching. I'll be back with another problem very soon. Till then, stay safe. Goodbye.